This is dealing with allylic and benzylic bromination, and basically the idea is that you can functionalize this further without actually disrupting the double bond. And so if you have a source of a radical such as a AIBN initiator, this is one of those reagents that you're just going to need to know. It's called azobis isobutyronitrile, and what it does is simply initiate a radical reaction by having the formation of nitrogen gas at the same time as it creates two relatively stable radicals. So this is material that you can use to safely initiate a radical reaction. So if you have some radical initiator and a source of bromine, like NBS and bromosuccinimide, where you have a bromide present, and again, this can react in radical-like fashion with homolytic cleavage, like that, or NCS and chlorosuccinimide, then you can do chemistry that essentially involves adding bromide via a radical process. The outcome here is going to be that you end up installing a bromide at the allylic position. We'll walk through the mechanism briefly in a moment, but you're going to have to form a radical at that position at some point. And this radical is going to be stabilized by resonance. In radical land, resonance may look a little bit more confusing and involve more arrows, but this is just essentially a resonance contributor. We should talk briefly about the stabilization of cations and how that relates to the stabilization of radicals. You already know that the general pattern is tertiary cations are more stable than secondary cations, which are more stable than primary cations, and that's generally speaking true. And what's going on there is you're stabilizing an honest-to-goodness empty orbital. So when you have a radical, you don't have an empty orbital, you have a single electron in that orbital, but it still lacks for electron density. And so you're still going to have the same general pattern, and for the same reason. Other things can donate electron density in a tertiary case. It's less crucial for a radical than it is for a cation, but the same general trend will hold. And as before, the presence of resonance essentially shifts you over one. So a secondary cation is essentially equivalent to a primary cation plus resonance. The same idea is true with radicals. What guides the reaction where the bromide installs is essentially resonance. And so what that means, of course, you can install the bromine on both sides of the initial material. Obviously, these two are the same thing, so there's no difference there. So by the same token, when you are looking at a benzylic chlorination, the benzylic position is going to be at the spot immediately next to the benzene ring. This is the benzylic position. So if you follow through the mechanism and figure out what happens, eventually what you realize is that the position right next to the benzene ring is going to be stabilized by resonance. So you'll make that preferentially over other stuff. Of course, you could choose to use a different initiator if you wanted. I also have listed here peroxides as the initiator. What could happen is simply homolytic cleavage of the weak oxygen-oxygen bond, which then leads to relatively stable radicals. The AIBN, you aren't fragmenting necessarily weak bonds, but what you do generate here is a nitrogen gas, which is incredibly stable and can simply leave. So that's the driving force for this one. So talking in detail about the mechanism of the bromination reaction, which again will lead to bromination at the allylic position, what has to happen first is some initiation. And so the initiation will involve the AIBN. This is the first part of the initiation step. What happens is that nitrogen gas leaves, and then what you form is two molecules of this tertiary, therefore relatively stable, and stabilized by resonance radical. So this is a really stable radical, and this is what forms when AIBN fragments. And again, you don't need very much AIBN, you just need a small amount, but when you simply heat this up in some neutral solvent that isn't going to participate, it fragments, nitrogen gas bubbles away, and what you're left with is a pair of these radicals. So this radical can go ahead and participate further in the reaction. Again, this is technically part of the initiation step because this has to then convert into propagating radical, which will be the main part of the chain mechanism. The second part of the initiation step, of course, simply involves conversion of this radical into the propagating radical, which for the purposes of this mechanism is going to be the succinimide radical. So the propagating radical for the remainder of the mechanism will be the succinimide radical. This is the result of AIBN fragmenting, and this is NBS. Of course, as I've already indicated up here, you can imagine this serving as an initiator. If you hit it with some light or heated it up enough, it could simply homolytically fragment in the first place. So regardless of how you generate the succinimide radical, the N dot, that is the key feature, this will then become the propagating radical in the chain portion of the mechanism. So what happens is that the succinimide will abstract the desired hydrogen here, and what will happen is that it will lead to a radical at the primary position, but primary with resonance. So of course, this is stabilized by resonance resonance, as I already showed. Once the allylic radical has formed, then the allylic radical will essentially encounter another N-bromosuccinimide molecule, and what it will do is make a bond to the bromide while again regenerating the succinimide radical. And so of course you can see that the succinimide radical is going to be the propagating radical in this mechanism. It is the thing that is involved in the reaction up here and then becomes regenerated after the second step. It gets used up in the first step of the chain propagation and gets regenerated in the second step of the chain propagation. So this is propagating radical. And then this just simply continues until all of the remaining starting materials have been used up, and then you have some kind of termination steps, and any combination of any of the radicals formed can be involved in those termination steps. So at the conclusion of the reaction, for example, you could have the remaining succinimide radical make a bond to a allyl radical, and that would be a perfectly acceptable termination step. You could have a allyl radical react with itself, and that would be a perfectly acceptable termination step. You could have the succinimide react with itself, and that would be a perfectly acceptable termination step as well. And I'm sure there are plenty of other termination steps that I'm failing to contemplate at this point. The point is, as always, that these always go via some sort of initiation, and the initiation step can take several steps as necessary. Then you go through a chain propagation mechanism, and then in the end, all remaining radicals will eventually encounter each other, and those are your termination steps. And basically all products that result from two radicals encountering each other are perfectly acceptable termination steps. The end result, though, is that if you take NBS and AIBN and mix them together with an allylic or benzylic carbon-containing substrates, then you can replace the CH bond with a carbon-bromine bond. If you do the reaction with N-chlorosuccinimide, then you'll make a chlorine there instead. So this is a way of introducing additional functionality. If you already have a double bond, then at the allylic position, you can introduce new functionality. Of course, if there are multiple allylic positions, then you have the issues with potentially what are your kinetic products, what are your thermodynamic products, and so on, because allylic and benzylic brominations always involve resonance. That will be a key feature of all of these sorts of reactions.